years ago, and is not even in the textbook that we teach. I don't really know why we even care about it personally, but let's just real quick talk about spectroscopy and the electromagnetic spectrum. So first off, we have an atom right here, and it has electrons that go around it. You okay with that? I'm sure you read and enjoyed all that stuff this weekend. All right, we mostly in this class talk about transitions when electrons move up and down because our eyes see visible light. All right, and we're in chemistry where we study mostly what happens with the electron. So energy can be given out, or electromagnetic radiation can be given out from an atom in 3 different ways. Do you remember what they are? Tell your partner. All right. So here we go. It sounded like I heard them. Vibrational, rotational, and through electron changes, right? The one we study most is when electron comes up, goes down, and releases light, or UV. All right, but the other 2 are when the atom rotates or when the atom vibrates. You with me? Okay. Now, there's not a real ton of deep information here, but they do expect you on the AP test to know these 3 things. We have microwave radiation. It is released when we have a molecular rotation. When atoms inside the molecule literally twist, and that changes their energy, and the energy change is released in the form of microwave radiation. You all right with that? Infrared radiation is associated with transitions in molecular vibrational levels. All right, so that's when you have the thing that is your molecule atom vibrating versus spinning. So like in your microwave that cooks food, it takes advantage of this molecular rotation, causes the water molecules to spin. That creates friction, which creates heat, which cooks your food. Infrared, molecular vibration, and ultraviolet visible is from electronic energy levels. Now, I have these highlighted, so just, I don't know if this will help you, but if you have Mr. IV, and I don't know, UV, just go with me here. Mr. IV. If you can memorize 2, you don't need to know the 3rd because it's the other one. Mr. means microwave, comes from rotational. Microwave, rotational. Mr. IV, where's that coming from? Infrared comes from vibrational. And then what do we have left? We have UV. That one, I don't know, that one's dumber. But ultraviolet or visible comes from electronic releases. Does that help at all? Okay, well, someone said yes, so that works for me. So this problem, what? Thank you. This problem was on the practice. You can see this lady from whatever high school right here. So this is UV. So what would be the next letter? E. This is infrared. And so we have IV. Microwave is Mr. So we have ultraviolet / visible coming from electron transitions. V, vibrational. And R, rotational. You okay with that?
When you shine a black light onto something, that's why it like glows.
It's because you excite the atoms or the electrons. Yeah. Weird. Yeah. They absorb that energy and then they give it off slow. So that's why it doesn't come right back out. It's bright, but they take the energy in They move things up and down and give off light over a long period of time, but less energetic light. Okay, does that help? Good enough? It's a very, very small part of this class that just fits in right here, and then we never really talk about it again. Okay, now today we're going to talk about quantum numbers and electron configurations. Quantum numbers are not really on the test anymore. Like, it helps to know them, but you'll not be assessed on them. They used to be very on the test. If you haven't read, keep reading. Objectives: gain a basic understanding of quantum numbers and electron configurations, and yada, yada, yada. You okay with that? What is this? This is the atom. This is what we think it looks like right now. So let's just go on like a 3,000-year journey. They used to think that the atom looked like this. Like, they didn't know circles or squares or rectangles or triangles or whatever. They just thought it was small stuff that couldn't be broken up. They didn't know very well because it was Democritus sitting on a rock in Greece. Like, he didn't have any tools. He's like, I bet this rock's made out of really small things that can't be divided. All right, then, what's that? Yep. Then Aristotle came along and he said, I think that this rock's made out of stuff that is infinitely divisible, that you could divide it forever. Okay. And then a guy named John Dalton came along and he said, I think that the atom looks like small spheres and that it's not divisible. Okay. Then a guy came along, his name was J.J. Thomson, and he discovered that an atom had an electron, something that could come out and had a negative charge. So he came up with a model called the plum pudding model. Does this sound familiar to anyone? All right, it was a circle of a positive blah, like, who knows, just a goo, like pudding. And then it had negative things in it like plums. It's called the plum pudding model. Once again, the pudding is positively charged, so the negative electrons are like the plums. Now, no one eats that anymore, so you can call it the chocolate chip cookie model, where the chocolate chips represent the electrons and the cookie holding everything together is some positive something. All right, then Ernest Rutherford came along and he discovered there was an actual nucleus when he did the gold foil experiment. So he came up with a model that looked like this. There we go. So kids, we call this the Jimmy Neutron model, where you have a positive nucleus and there are electrons flying around it. Okay with that? Thomson's model had a problem though. He could not explain, based on his physics, he couldn't explain why the electron, which was negative, didn't just spiral into the nucleus. So his was kind of, I mean, we were getting closer to a Ritter model, but not the right one. Okay, along came Bohr, and Bohr took all that quantization stuff and he said, all right, there's a nucleus, we know that. There's electrons, we know that. They do not fly into the nucleus, we know that, or matter wouldn't exist like we know it. So he said, all right, electrons live in orbitals, or orbits, I should say technically, and they can live there, but there's a minimum amount of energy that an electron could have based on its distance from the nucleus. It cannot be less than that. And that is like, oh, okay, well, that explains why it can't go in, which to me, I'm like, that doesn't really explain anything, but great. All right, electrons can live on specific orbitals. They can move between them, but they are never really between them, like stairs. Go ahead.
So what stops the electron from going?
That's still a really great question that no one has any idea. Yep. He's been positive with COVID forever. All right. I don't know. Okay, so Bohr was super right, and his math is super right, but he's also way wrong. All right. And so they did more studies, more math, and they've come up with the nucleus is still positive. It has protons and neutrons in it. And instead of electrons living in orbits, electrons live in orbitals, which are three-dimensional shapes on a graph that are answers to a really complicated math equation called the wave function. What? No, well, everything I'm talking about, you are learning, but you don't have to do the math. The wave function is really complicated. Okay, so what they did, and we'll talk about it more, but they discovered, they did this math, and they have the nucleus, and they said, okay, well, an electron lives somewhere inside this area. Not really an area, volume. Okay, well, that's three-dimensional. If you have one electron, it's there. If you have two, it's right here. But if you have more, the probability of finding one of them expands. And the four of them are in here somewhere, maybe most of the time, probably, but not all the time. Okay? They're probably here. We don't know the location of electron anymore. We know where it probably is. And then they came up with math and it said, hey, if you get 6, they're probably somewhere in one of these clouds. And if you add 2 more than that, a bigger circle that they live in. And you add more than that, a bigger one of these. And if you do that, you go here. They're really pretty flowers. I better group this and shrink it all. You know what? I have a button right here. Do that instead. Okay, and I don't know where we're at, but we're about there. And so you add 2 more. We'll go red for these. They live somewhere here, but then you add more, and they're somewhere in 5 of these. Okay, and then you add 2 more, or sorry, then you add 6 more, and there are more of these. All right, and then you add 2 more, and they're a bigger circle, and then there are these, and then there's some that look like this. All right, and there's this, they're in 7 dimensions, and boom, there's your atom. It's just right there. Super easy. So, and all this is saying that if we have an electron in an atom, it probably lives close to the nucleus, but it could be here. But guess what, though? Could be at betas. Like right now, I'm going out of order here. Do your parents know where exactly you are right now? No. Does any of your parents know the seat you're sitting in this classroom? No? Okay. Yeah, one of them may. Raise your hands if your teachers at least know you're in AP chemistry right now. Okay, so there's a handful. There's a handful that know that you should be in this room. Ryan, have you ever not been in this room 4th hour? Okay, so most likely we can find Ryan at this time of day in this room somewhere. And really, if I'm going to look for him, I'm going to start at that chair because the probability is the highest it'll be in that chair, right? And the probability that I find him decreases the farther I move from his chair. But could I still find him on the football field? Sure. He probably isn't going to slough, but I could find him at Beto's. Chick-fil-A? Well, I could. So we don't know. We've accepted in this world that we don't know exactly where the electron is. We only know where it probably is. Just like your parents, they don't know exactly where you are right now, but they would start looking at the school and the probability of finding you would decrease the farther they went away from it. Okay, you are the electron, school is the nucleus. We don't know where an electron is specifically, but we know it's probably close to where? The nucleus. And the farther we get away, the less likely it is to find it. Okay, we're going to come back to all that. Will you remember some numbers for me? Remember 2? What other numbers did I say? 6? Okay, I did say 5. 7. 8. Remember all these numbers because if I do today right, and you paid attention, and you like sort of are at least a B+ at heart, because a lot of you got A's, you know you didn't earn it, but like at least a B+ at heart, you're like, oh, today's going to click, and you'll never see that piece of paper the same ever again after today, if I do it right and you're with me. Okay, so here we go. This is really complicated, and I forbid you from writing anything on that slide down. Hmm? Thank you. Okay, Louis de Broglie. So at this point in time, it's okay. He's the baby's cousin. Louis de Broglie. Why is that funny? Even 1%? I don't know either. Okay, here we go. At this point in time, we sort of believe, we're like not in this class, but like in history, we're with the Bohr model. And Bohr's math is 100% true. Bohr's math that if I'm on this table and I fall off, it's going to hurt that much. That's true. But we're not on tables anymore. I'm probably in a room, maybe if I feel like it. Okay, and instead of falling to like a different rung, our probability cloud changes shapes or size. I know, just go with me. But it's changing, and it's actually a really genius change. So here we go. Louis de Broglie, he came up with the idea, that's what positive means, that if light can have material properties, matter should exhibit wave properties. And he demonstrated that the relationship between mass and wavelength was that we don't need to care about because we already did that math. You okay with that? But he's starting to say matter and light are actually kind of tied together, which is super weird. When we talk about this stuff, it's called quantum mechanics, and we're talking about the smallest parts of matter. Because I am a human that weighs too much. I gained a little weight over the break. Okay, I'll suck in while I teach. I did nothing but drive, watch football, eat food, and drink pop. That's how you gain 7 pounds in 7 days. All right, some of you could use that. But anyway, I am a massive thing in the scale of what we're talking about. These, we're talking about like 9.11 times 10 to the negative 28 kilograms. That is the mass of an electron. Now, it's matter, but it's so small, it can behave like light. And that was what de Broglie said. All right, moving on. The uncertainty principle is one of the most confusing ideas on the planet. Don't. I told my wife one year, I'm like, I really think I need to study and get better at the uncertainty principle because I don't really get it. And she's like, so you're uncertain on the uncertainty principle? And I said, yeah, girl, you go. It's sort of weird. Yeah, and then she looks at me like I'm an idiot. Then I'm like, what's wrong, bro? And then she slaps me. No, I don't really. But okay, here we go. Heisenberg, he showed that the more precisely the momentum of a particle is known, the less precise its position is known. Don't write this down. You don't need to know this. But what he's saying, momentum, it's just easier to say it's speed. And they're related. Momentum is your velocity times your mass, but whatever. So he said, the more you know the speed, the less you know where it is. And I want you to think about something. Think about the last time you got a speeding ticket. Anyone willing to admit they have one? I'm the only one in the room with speeding tickets. Some of you are liars. Okay. Okay, well. The last ticket I got was 1994. So don't like at me that I'm a terrible driver's ed teacher. You were negative like 20 then. Okay. Stick with me. When you're driving along, just minding your own business, maybe accidentally going over the speed limit. A little bit. All right. A few. Here's the policeman and here's me. I'm not going to drive a car because I'm not good. The policeman's going to shoot his little radar gun, right? And then it's going to bounce off me, right? And it's going to change the space between those waves, depending on how fast I go. Are you okay with that? Okay. So in order for him to know my speed, what must I be doing? I must be moving. All right. So in order to have speed, what's your position? It doesn't exist. You cannot have a position if you have a speed, because in order to know speed, your position changed. You with me? Oh, so when you get a speeding ticket, guess what? Two things are written on that piece of paper. Your speed and your location. But officer, you can't know both. Because if you know my location, then I wasn't moving. If you know my speed, then I'm not where you say I am. Yeah. He's like, walk this line real quick. Like, no, I'm a good dancer. I'm just drunk. So this, now, there's a problem. What I'm saying is true. The policeman cannot know your location and your speed. But here's the problem. The larger you are, the more accurately you can know both. And a car compared to the size of an electron, pretty different, right? Okay. If you were in an electron and you're just cruising around, here's what would be cool if you're an electron. Follow this logic. Here's the electron, just minding its own business. And you, now just, I'm not an artist, okay? This is your eyeball. Okay? Yeah, I am looking at this electron. Light works. They used to think light went from your eye to something and came back. Did you know that? But no, that's what your headlights do. But your eye looks at light that came from something, right? So what is light? Does anyone know that we've read enough? Photon. It's a photon. Now it's a wave and a photon. It's both. How you know that? Okay, so a photon. In order for me to see or observe an electron, a photon has to just come chilling, hit it, and then come to my eye. All right. And then once this comes to my eye, I can say the following sentence. I know 100% where the electron is not. It was moving. And how big is a photon? It's about the same size. So when the photon hit the electron and bounced here, where'd that go? It's gone. When I observe and we find an electron, all we really know is where it used to be, and for sure it not is. It is not. It's gone. 1 second. So, do we ever know the location of an electron? No, but we do know where it was and where it probably is going to be. Where's it probably going to be? Close to the nucleus. Is it for sure? No, but I'll start looking there because that's the highest probability of finding it. Go ahead. Where do photons come from? They come from the sun. They come from anything that emits light or energy. So they come from atoms, anything like that. But like these lights, they're producing photons. It's just how light is produced, anything that gives off light. Okay, so the uncertainty principle says I can't really know where it's at if I know how fast it's going, and I can't know how fast it's going if I know where it's at. No, I just said the same thing, but you know what I meant. You can, but then you go to jail. Okay. Yeah, it's right. So here's the deal. The smart officer would say, Well, you are correct, sir, but remember, mass is part of the uncertainty equation. And since your mass is 4,000 pounds, all right, I can know your location within like a micron or something like that, like which is 10 to the negative 10. But if this is a negative 28, not exactly, yep. If it's negative 28, then the uncertainty is huge. Okay, we don't know. The smaller something is, the harder it is to know where it is. And that's easy enough. You lose the back of your earring in the classroom. Did that happen to you? But it's hard to find, right? How come? Because it's small. Aisley falls over and we're like, where'd she go? We can probably find her. Like, oh, she's right there. All right? Because she's massive is how we describe it. All right? Yeah, every girl wants to be called massive, right? You should meet my girlfriend. She's massive. Like, she's not gonna be your girlfriend long. All right? It just means like you're significantly larger than an electron, which everyone in the room, I should have chose a boy. I'm sorry. Okay. It was not. Okay. So how do we feel about this so far? So basically, de Broglie, I will. De Broglie and then Heisenberg basically proved that Bohr's model could not be correct. We knew the math was correct. All right. So Schrodinger takes all this, Schrodinger, he takes all this information and comes up with his theory. Right? Now, how have you heard of Schrodinger before? The cat. What about the cat, Tim? Yes and no. We don't know until we open it. Okay. So Schrodinger, he has this experiment. He comes up with all these things, and he's known for his dead cat experiment, or is it that we don't know? All right. And there's a lot of principles in science where we can't know something without destroying the very thing. Like your porcelain piggy bank when you're a kid, you can't know how much is in there unless you break it. Who has patience to shake out $25 of coins out that slot? Okay, one of you does. Oh my, you break it. Okay, anyway, here we go. I've wasted too much time. So Schrodinger comes up with this mathematical treatment where he takes all the characteristics, makes them variables, plugs them in, and comes up with what is known as quantum mechanics. It comes from what we call the wave equation, and it gives us the probable location to find an electron. Him and Chuck Norris. All right. Now,
he'll tell you a whole story about it too.
Probability clouds, they're not like perfect. This is a spherical cloud, but it really isn't a perfect sphere, but we're going to draw them as if they are. You okay with that? So these are answers to the wave equation when you put in a 1 or a 2 in for n. Now, you don't need to know what that is, but whatever. These are the answers on a 3-dimensional graphs. What's that? Yep, pretty much. Now, there's n is a different value as well, but in that sentence, it was just a number of electrons. Okay, so here we go. I've seen this before. Let me see what the next slides are. I'll come back. Okay, so the wave equation is designated with a lowercase Greek psi. And now you're not really where you need to write anything down still. You're like, Davidson, you're wasting my time. Well, this is cool crap. Sorry if you don't like it. You have the chance to transfer. All right. So the square of the wave equation, psi squared, gives a probability density map of where an electron has a certain statistical likelihood of being found at any given instant of time. Is it there? We don't know, but we think it probably is. It could be here, there, could be here, there, but the highest likelihood is near the nucleus. You with me? Could be, but it's probably over there because there's really no reason why the electron will be here. It's negative and it wants to be by a positive, which is dead center. Okay. Now, these clouds, if you remember, I drew some shapes. That sound familiar? Let me draw this again. So I said we had a nucleus and then we had a circle, correct? And then a circle. Anytime, this is, you should write down.
Okay.
Or just get it. But this is valuable. Like this is stuff you got to know. Anytime an electron resides in a spherical cloud, it's labeled with an S. Just gotta go with me. And the first person that says I learned this in Bert's class gets this right through their eyeball.
Okay, I learned it from Broglie. I
You
don't have to go to work.
have glasses. All right. Now, just kidding. I know you learned it in Bert's class. That's great. And I'm excited that you did. But you're going to learn it again. If you haven't had Bert, raise your hands. There we go.
He's great.
Oh, he's the best teacher in the school.
He taught me
Awesome.
the first 10 presidents of the United States.
Yeah, like with the walls or some black magic. Okay, well, enough of that. I have a Bert complex, okay? Okay. When you're drawing your atom, if it's a circle, what letter are you going to call that? An S. It's S for spherical, if you feel like writing that. It doesn't really relate, but whatever. Okay, who remembers what the next thing was? Who jumped ahead and knows the letter? P. But what shape was it? Do you remember? It was the pedals, or I call them propellers. The book calls them dumbbells. It's okay, doesn't matter. Okay, now, please look. These pedals, I drew them like one up and down, one left and one right, and then one like at an angle. That's the one that represents in and out of the board. You're kind of okay with that? So how many of the propellers did I draw?
6.
No. 3. Because the propeller on a plane isn't just that part. You would not fly very well. All right? It has that. You with me? So the next are these. I'm going to erase this for a second. Well, not for all time. Okay. And there's 3 ways that P's are oriented in the wave equation. Now, remember, these are just plots on a 3-dimensional graph. If it's an S, it's likely to find them here. If it's a P, you're likely still to find them here, but there'll be some here. Lots and lots, and kind of descending as you go down. You okay with that? These are areas, or not areas, they are answers on a 3-dimensional graph of the wave equation. All right. And we draw these shapes to kind of represent them. Like, oh, hey, the blues kind of filled a circle. These greens kind of filled this area. It's confusing. I'm aware of that. Okay, we have P, and there are 3 of them. All right, who remembers the next one I drew? I kind of just scribbled this one. All right, I call them 4-leaf clovers or popcorns or flowers or whatever you want. All right, I only said it once, but I said, and there'll be, how many of these? 5. Good job. Save that number though. There are 5 of them. The popcorns are oriented in 5 different orientations of space. I kind of ran out of space, but whatever. You with me? All right, that's a good question. These are called D. Don't make no sense. Okay. So far, you with me? We have S. That's the circles or spheres. All right. How many did I draw? One. Good. Thanks for asking because I did forget. S, there's just one. Now it will repeat. Do you remember? I said I drew a small one, then I had a bigger one. Any idea what we call the first one? 1S. What would I call the second one? 2S. And yes, it's the boxes. You're like, why is he wasting so much time? It helps in the long run, I promise. Okay. Then you remember I drew these small, and then I added another circle, and I drew them bigger, right? All right. So I got the 2P's, or the 3P's, or the 4P's, or the 5P's. These are D's. You with me? Okay. Then I drew one that was really weird, and it's not super accurate at all, but we're just going to go with it. What was the weird one? You remember? All right. It had a loop, a donut, and a loop. I call these F's. Now, that's not super accurate. No one exactly knows what an F cloud looks like. All right. So yada, 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 yada. I said this number one time, I think. 7. Okay, now, are we ready? Okay, here we go. Can someone tell me this? What is 1 times 2? 2. What is 3 times 2? 6. Oh my. What is 5 times 2? 10. Oh no. What's 7 times 2? 14. All right. I need some help. Okay. Then you go stand over there. Yep. All right. You grab that corner right there. Oh my laws. All right. Yeah, we need tall people actually. All right. We could use someone in the middle too. I'll go in the middle. Here we go. You hold this. Well, okay, you come here. You're right here. You're right here. You hold the middle. Okay, hold on. Here we go. Here we go. Please stick with me right now. Are we ready? This area of the periodic table has a name. You're gonna fail. Anyone know what they're called? No, it's a different name. I know. You're like, wait, it is. This area right here, the 2 columns here, are called the S block atoms. How wide is this? 2. Stick with me for a minute. Over here, move. Back up. Okay. This area right here has a letter that denotes when atoms are from here. Any idea? P. How many was in the P? 6. How wide is this? It's 6 wide.
Does that mean there's 14 metals in the middle?
There's 14 metals in the middle. Sort of. Here we go. This is the D block. Don't let me hit you in the face. This right there where the spiders are, you with me on that one? These pink ones are called the D block elements, and their electrons fill the D shell. D was the popcorn and had how many orientations? 5. And each orientation can hold a maximum of 2, for a total of 10. 1, 2, 3, 4, 5, 10. Well, where are the F's at?
The weird bottom row.
The bottom ones, which aren't really on the bottom. That's why I have this giant periodic table that I should have looked how big it was before I ordered it. It was supposed to go there, but it's too big. The F's are here, and they're not under, they're in here. F's, you guys are great. F's are in how many orientations? 7. And each one can hold 2. So how wide is this? 14. All right, you guys can put that down somehow and walk away.
I wasn't ready.
All right, go, just drop it. We'll be good. So listen. Quantum mechanics came along in the 1920s and 30s. The periodic table was organized in 1863. And all quantum mechanics did was prove that this was put together exactly right. So how on earth in 1863 did they organize something that has to do with this crazy crap and scribbles that we drew on this screen? How would they relate to each other? Because the number of electrons, a little bit more specifically. You're right, there's one word missing. Valence electrons. The number of valence electrons. Everything in family 1 and 2, if you're in family 1, has 1 valence electron or half of its circle filled. It doesn't like that. It's unhappy. So it's going to either fill a circle and 3 propellers or just kick one out. Which one's easier? Kick it out. So metals are what? We've said it 100 times. Losers. It loses an electron. It loses it violently, right? Really violently. You would like to see that. I've never shown it, right? Okay, well, let's blow some crap up. Hold on. Blow it up. Blow it up. Okay, hold on. All right, now hold on. Did Mendeleev know about valence electrons in 1863? Nope. Mendeleev had no idea about valence electrons. He only had observations, and he knew everything in family 1 was really reactive. Everything in family 2 was pretty reactive, but less reactive than family 1. 3, kind of, but boring. 7, awesome. 8, ain't nothing happening with no one ever. All right, and so he organized them based on observations, and these observations have everything to do with the number of valence electrons they have. Get over there. Okay, so here we go, my friends. Might break my shoulder. Oh. Okay, now, what you're thinking is he needs to clean that. I have. It's burnt. So it hasn't been treated nicely in its life. Okay, I'm just going to go ahead and cut to the chase, if you're okay with that. Oh, they're over there somewhere. Exactly. They're probably over there somewhere. Okay, I put in phenolphthalein that should be clear, but it's not clear clearly, but whatever. Okay, I will put some just potassium. Sandra, hit the lights for me. You can record it, that's just fine. I'll do it twice. Okay, so it goes pretty quick. Did it go quick?
Yeah, and it looked purple.
Oh, and it turned it purple. Okay. We are already dead. No, we're not going to die. Okay, so family 1, water, really reactive. Okay, here's the second piece. It's a little smaller. I doubt it will pop as fast, but it might.
I'm sorry, I'm so fast. I saw a little bit.
Whoa. That one?
Yeah, that one I didn't mush as much. I need the fan on, so hold on before we have to evacuate the school. All right, so what? Yeah. Okay, now I'm not going to do the other ones. They're a little bit more boring, but I'll show you a video real fast that has to do with just this crazy model of the atom. And I burned my giant, super useless periodic table. Yeah, it's rubber, so it just melted. All right. No. Okay, are we ready?
Cesium and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time, we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
So what do you think? One of my favorite definitions of all of chemistry is, as you can see, they become gradually more terrifying as we move lower in family one. Okay, so what we're talking about is like quantum mechanics, but it has everything to do with why that stuff blew up. Now, there's a little more to it, but the periodic table organized based on what was seen, and eventually what was seen was proved in the math, and it's really cool. There's hardly anything else in science that hasn't changed since 1863. It's a long, long time ago. Okay, coming back to this. You're like, all right, that's great, but everything about this is everything about the structure of the periodic table and the boxes that we're going to talk about. Okay, now I'm going to blow through this. This is from regular chemistry slides right here. Elements are arranged on the periodic table according to atomic number. You know that, right? Next, the atomic number corresponds not just to the number of protons, but also the number of electrons. We have to know that. This process we're going to do, where we write the address of where the electrons live, if we don't know how many electrons there are, then we can't do this whole process. So the key first is to know, hey, if I'm at oxygen, I have 8 electrons. Are we okay with that? Can you all find that number? You're in AP, so I assume you can. Next, the arrangement of electrons in an atom is called the electron configuration. And it's based off of these quantum numbers, even though we never teach quantum numbers in any other class but this. but it all comes from the math that you don't have to do. You just gotta trust whatever I just said was sort of true. All right. Now, everything in nature wants to be at its lowest possible energy level, just like you guys. All right. You don't want to do more work than you have to. Neither does an electron, which means its negative lazy butt wants to be close to what? The positive. So in our world, gravity keeps us down. Right? I'm lazy. I lay down. That's when my potential energy is at its lowest. That's where I am the most stable. Can't fall over if I'm laying down on the ground, right? If we are elevated, we become less stable and gain potential energy. An electron wants to be as close to the nucleus as it can. That is called its ground state, and that's where it is the most stable. So an electron wants to be by the nucleus, never in it, all right? They still have really no concrete knowledge to absolutely why it doesn't go in, besides it can't, all right? But scientists are parents too. Why? Because, all right? We don't know, but we know it doesn't. Okay, so electrons want to be close to the nucleus. All right, so yada, 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 we don't care about that. So the most stable or ground configuration of an atom is that in which the electrons are in the lowest possible energy levels, or how I summed it up here, as close to the nucleus as possible. That's where the electrons want to live. So all these probability clouds, no matter what shape they are, really the electron wants to be as close to the center or the nucleus as possible. Even if the shape is one of these crazios, all right, it still wants to be as close as it can. I have no idea. Yeah, that's not even the right answer. It makes sense, but who knows? All right, here we go. Now, the orbitals of an atom are arranged in order of increasing energy. So the smallest one is the closest to the nucleus, and electrons there have the lowest amount of energy. It's just like you're on the bottom rung of a ladder. It will hurt the least when you fall. But it's not a ladder. It's a sphere that you're in. And if you were to fall, you wouldn't really lose any energy. Okay. Now, when we draw them, if I draw an atom, I have the first S, the second S, the third S, the fourth S, the fifth S, and whatever. Well, how do we draw them to denote they're different? No, it's a stupid question, I guess. They're just bigger. They're just bigger. All right. The first one is only accounting for 2 electrons. The second one is accounting for 2 electrons, but there were already 2 electrons. Because you can't get to the second S unless you've already come from the first. This one only holds 2, but by the time you get there, there's already 10. So they get bigger and bigger. All right, this number right here, any guesses what it refers to on the periodic table? The row. So if I was talking about potassium, potassium lives in the first 2 columns, right? Which is the S block, and what row? 4th. So I would know potassium's valence electron is a 4s, and is it in the first one or the second one? It's in the first one. I know its address based on its location. Well, and guess what? What if I had 3s2? What atom am I talking about there? Magnesium. So I can know who it is based on its address and vice versa. So this tells me right here, I'm talking about an atom in the 3rd row of the periodic table in the S block, and it's the second one over. Thumbs up-ish? Okay. This will annoy some people, but really we aren't even what's on the test yet. It's fine. Okay, so here we go. What time are we out of here? Anyone know? What? 2 minutes. Dang it, Tom. All right. this is one of my favorite slides of the entire year. Here we go. I will finish with this and start with it tomorrow. In the quantum mechanics model of the atom, the principal energy levels n equals 1, 2, 3 of an element orbitals are divided into sublevels based on the energy and electron release if it should fall to the ground state. Okay, what does that even mean? It says that the rows of the periodic table are divided into sections. They are divided into S's, D's, F's, and wrong way, Tom, and P's. Well, helium like lives here and there. It's a shapeshifter. It's a 2s. Yep, and hydrogen lives here or really could live here. Yep, it can. So one more time, that sentence was saying that the rows of the periodic table have different shaped clouds based on the energy and electron release if it's changed shapes. We'll come back to this tomorrow. Hopefully it helps. And then we'll do the boxes and you realize he spent a whole day on something that takes 30 seconds. The answer is yes. And you're welcome. Thank you.